Splitting a large application into smaller pieces provides no inherent guarantee of better performance. When a monolithic codebase shatters into dozens of disconnected fragments, the underlying logic is simply distributed, not accelerated. This transition replaces localized execution with the physics of a distributed network. Memory calls that previously completed in nanoseconds become HTTP requests traveling over wire, now subject to latency, packet loss, and unpredictable routing. Without strict architectural boundaries, these independent fragments often devolve into a distributed monolith. When Service A cannot process a request because it is waiting on Service B, a failure in the dependency cascades backward, exhausting the resources of every upstream caller. To maintain availability at an enterprise scale, we are going to architect a .NET 10 system from the ground up. We will implement 10 specific microservice patterns, deploying the same core logic across both AWS and Azure infrastructure. Managing state and partition tolerance in these environments requires moving away from a strictly code-centric view. Success depends on using patterns as the primary mechanism for controlling network unpredictability. Direct external access to discrete internal services decentralizes security and creates high coupling. This forces every individual node to manage its own authentication logic and ties the client application to your specific internal network addresses. The API gateway pattern resolves this by acting as a unified facade. It absorbs the external impact, centralizing JWT validation and rate limiting before routing organized traffic to the appropriate internal node. Inside the network, cloud IP addresses are ephemeral. As instances scale or recover, hard-coded endpoints inevitably break. Service discovery uses registry and heartbeat patterns. Nodes ping a central registry table with health statuses, letting the gateway dynamically map routes to healthy instances. We implement this registry using AWS Cloud Map for Amazon environments and Azure Container Apps DNS for Microsoft stacks. Both services use the same heartbeat mechanism to maintain a live map of the cluster. Securing the perimeter and dynamically mapping internal routes decouples the front-end client from the back-end deployment topology. The internal network can scale or relocate without interrupting the external connection. To prevent single-node bottlenecks, we apply Pattern 3, load balancing. This ensures that inbound traffic is distributed across redundant instances, maximizing throughput. Even with load balancing, a cluster remains vulnerable to cascading failures. If a downstream dependency times out, upstream services keep sending requests, hanging their threads, and exhausting the entire cluster's resources while waiting for a response. Pattern 4, the circuit breaker, isolates these failures. Hitting a failure threshold switches to an open, blocked flow, protecting the struggling node. After a timeout, a half-open state allows a single test request. If successful, the circuit closes, restoring traffic. For business processes that do not require an immediate response to the user, we can eliminate synchronous dependencies entirely by using Pattern 5, event-driven communication. Using pub submodels and message queues decouples producers from consumers. The producer emits an event and moves on, while consumers process data at their own rate, allowing both to scale independently. Because cloud messaging often results in at least once delivery, an event might be sent twice. We use the idempotent consumer pattern to ensure that duplicate messages are identified and ignored, preventing database corruption. Stripping away synchronous HTTP calls and enforcing circuit breakers physically isolates service failures. This creates a resilient network where a localized crash does not paralyze the entire system. Performance will degrade at the database layer if a single data store is forced to handle high-throughput reads while simultaneously processing complex transactional writes. Pattern 6, CQRS, separates conflicting workloads into two pipelines. The write pipeline uses relational systems like Aurora or Azure SQL, optimizing for transactional integrity and complex logic. The read pipeline uses document stores like DynamoDB or Cosmos DB, serving concurrent queries instantly without resource contention. To keep the system synchronized, the write model emits domain events. These events trigger projections that update the read model, ensuring eventual consistency across the datasets. Adopting polyglot persistence and CQRS allows each database to scale according to its specific workload profile, resolving the resource contention found in unified data stores.
When a process spans multiple services, like coordinating an order across payment, inventory, and shipping, using legacy two-phase commit locks across databases is too slow and unreliable for the cloud. Pattern 7, the Saga pattern, uses a sequence of isolated local transactions. A central orchestrator coordinates the flow. If a failure occurs at step 3, the orchestrator issues compensating commands that systematically roll back preceding steps, returning the system to a consistent state. We manage this state logic using AWS step functions or Azure durable functions, which provide the persistence necessary to handle long-running business processes. Sagas prioritize availability over immediate consistency. In a distributed environment, this eventual consistency is a required trade-off for maintaining a highly available system. As services grow, operational boilerplate for MTLS encryption, retries, and telemetry becomes a burden when embedded inside every microservice node. Pattern 8, the service mesh, offloads these concerns. Every node pairs with a sidecar proxy that intercepts and routes all traffic. Infrastructure layers like AWS App Mesh or Azure Dapper enforce MTLS encryption and retry policies at this sidecar level, bypassing application logic entirely. By injecting correlation IDs at the gateway, we implement Pattern 9, distributed tracing. Using AWS X-Ray or Application Insights, we can track request latency as it moves through the mesh, mapping the complete path of every call. Pattern 10, containerization, standardizes the package. Using ECS Fargate or Azure Container Apps, we deploy decoupled nodes as immutable units running consistently across any cloud environment. Moving cross-cutting concerns to the infrastructure plane creates a zero-trust environment. The mesh handles the network, allowing developers to focus their efforts strictly on domain logic. This 10-pattern framework provides the structural foundation for a resilient enterprise architecture. While implementations differ, mapping AWS services on the left and Azure on the right, the architectural patterns are identical. Whether using DynamoDB or Cosmos DB, the CQRS requirement remains the same. The core .NET 10 application logic remains identical, fully agnostic to the surrounding infrastructure. Using solid principles and dependency injection allows us to abstract the cloud provider. The application depends on high-level abstractions, while the specific cloud services are injected as implementation details. Internalizing these fundamental computer science patterns provides the structural blueprint for building resilient systems, regardless of which cloud provider hosts the workloads.